Hello and welcome to ICDD's in-session webinars. Soon you will hear Professor T.N. Guru Rao present A Pictorial Approach to Comprehend Symmetry in Molecules and Crystals, Part 2. Please remember to visit icdd.com for information on future free webinars, educational events, product information, and to purchase ICDD's databases and software.
As is mentioned, that we now cover the part 2 of this session, which is on a pictorial approach to comprehend symmetry in molecules and crystals. We talked about parts of this in the first part, where we discussed the concepts of symmetry and the requirement of symmetry under many circumstances, whether it is art or science or whatever, and brought in the issue of solid state. And we discussed several aspects that are related to the basis of symmetry, worked out the rules and regulations which one has to follow. And then we brought up the point group idea, and then talked about the restrictions in the rotation axis as a consequence of translational periodicity. And then took the translational periodicity as for granted in solid materials and looked at the various point group symmetries that come up. And we also looked at it from the point of view of reducing the 3 dimensions to 2 dimensions by taking stereographic projections. And in the stereographic projections, we identified the symmetry elements based on the location of these projection points of the objects. So we have been discussing it with respect to objects, but with the condition that every point in the 3-dimensional space finds this symmetry. That means if there is a symmetry 1 bar that is associated with a point, then it is all over the 3-dimensional space. With that concept, we developed further the various crystal systems which come up as a consequence, which essentially involves the unit cell concept and the 7 crystal systems. Then we talked about the 32 point groups. So we brought in these numbers, 7, 14, 32. And then we were at the stage where we were talking about the 230 space groups, at which time we decided that we will go to part 2 because of time constraint. So before I start, I must tell you that there is a very interesting city fair which is going on outside the street. There's a lot of noise which you will hear on and off. I've tried to minimize the noise as far as possible, but I'm pretty sure you will listen to that because there's a lot of noise going around using bugles and trumpets and whatnot. And this is a fair in which people from all around villages around Bangalore, they bring these peanuts in large quantities, and then they display like this. And you see heaps of symmetrically arranged, I would say, the peanut mounts. And these mounts are now sold at reasonable prices because it is affordable to common man. And you can see this goes on and on for probably a half a mile up the hill, which is just about 100 yards from my house. And this goes on for 2 days, yesterday and today, and it ends late tonight. It is not just attracting the local people, it also attracts quite a few foreigners, and it's become now a tourist attraction, as can be seen from this slide. So I just thought that I will show you these 2 slides and tell you the cause for the noise in my background is because of that. All right, so we had stopped at this slide, where we were talking about the symmetry that is associated with the least symmetric 3-dimensional unit, which has the translational periodicity, and it can be described in terms of A not equal to B not equal to C, the 3 directions. Alpha, beta, gamma are not equal to each other. No need to say 90 here. And then the corresponding stereographic projection of objects which go into this kind of a system are shown on the left side here, 1 and 1 bar. 1 bar representing the center of symmetry. The center of symmetry is situated and the notation for that is an open circle at the center of the circle. We then call this repeat unit as a primitive unit, and the number of lattice points that are associated with this, we count every edge of the lattice, which is shared by 8 others, and therefore we call it as the total number of lattice points, we count it as 1. Further, if we have this 1 bar symmetry, for every point in x, y, z in this space, we will have a corresponding minus x minus y minus z. And these are referred to as the general positions, and the notation that is given is z is equal to 2. As I mentioned in the previous lecture, these are the basic elements of grammar. We learned the alphabets and then the words which build up the language. And then we eventually use the combination of words to bring out the meaning in the language. So it's like language learning. We learn the concepts of symmetry in case of solid materials, which is restricted to solids as we already discussed. We also brought up towards the end of the talk last week issue of special positions. In this particular position, I've given z equals 1, but we will discuss this in more detail as we go along in today's discussions. The next one, which is the next symmetric object, is the monoclinic unit cell. In this, the objects that have to exist in this kind of a situation where A not equal to B not equal to C, and the 2 angles are 90 degrees to each other, will have to obey a minimum 2-fold symmetry. That means for every point x, y, z, there is a corresponding minus x, y, minus z. And the stereographic projection is depicted like this, 2x marks showing the presence of the 2-fold axis at the center. The notation for the 2-fold axis is shown here. This, in addition, we have 2 other point groups which can be associated with the monoclinic symmetry. They are the 2 bar, which is the mirror, where the 2-fold operation is combined along with it inversion center. So x, y, z and x, y bar z, that defines a mirror. 2 bar is a mirror. A 2-fold followed by a mirror symmetry. But a 2-fold and a mirror which is perpendicular to that is shown in the next one, which is the 3rd possible point group symmetry that gets associated with a monoclinic system. So these are the 3 symmetry elements which have a single rotation axis. And using the single rotation axis concept, we define the symmetry that is associated with a monoclinic symmetry. We also defined towards the end of the discussion last week, the presence of the 14 Bravais lattices. And there are 2 Bravais lattices which belong to the monoclinic system. They are P and C. And when we want to go to C, we just add half, half, 0 to each equivalent point among the 2 bar and 2 by M symmetry. And the depiction of these points, how they appear in the unit cell, is the one which we will have to discuss next before we go into see how we read the international tables. Later on, we will see that the international tables, when we read, we have all these issues which are clearly and fully described in the form of pictures. And what all we have to do is look at those pictures and decipher all these issues. The point group, the crystal system, and the information about the Bravais lattices, and therefore the equivalent points and the space group. The definition of the space group is obviously clear, just like the definition of the point group, which we gave last time, that if we take a point x, y, z, operate a 2-fold symmetry for the point group, we get x bar, y, z bar. We once again operate the same symmetry element on that particular point. We go back to x, y, z. So these now define the elements of a group, and therefore this is referred to as the point group. The same logic applies in the case of the space groups as well, as we will see as we go further in our discussion. This particular slide shows the way in which the objects can be arranged. We take the P1, of course, is obvious. There is only one point, so there is no need to discuss where the object could be. The object can be anywhere inside the unit cell. This is a projection down, let's say in this case, it's a y-axis down this direction, A, and in this direction it is B. C is coming towards you. Then any object can be represented. We represent that in this form. a comma with a positive saying that it is coming up towards us. So this represents the equivalent point, as we call it, the x, y, z. That is the equivalent point. So the object is now represented by that. Suppose the object is two atoms, let us say a diatom, then we will have two coordinates, x1, y1, z1, and x2, y2, z2. These two coordinates are referred to as fractional values associated with the positioning of the atoms. So these are fractional coordinates. So the two atoms, therefore, now will be looking at the origin and where there is a center of symmetry. The presence of the center of symmetry now takes this object and inverts the object. So plus goes to minus and the object gets inverted. So this now gives us the second equivalent point, which is outside of the unit cell, but we can always bring it inside the unit cell to complete the requirement of number of equivalent points by shifting this by 1 unit along the B direction, 1 unit along the A direction. This automatically creates a center of symmetry at this position, which is half-half. In this particular projection, it is half-half-half. So we therefore see that there is an equivalent point, there is a center of symmetry at 0, 0, 0. An additional center of symmetry gets created here. Likewise, additional centers of symmetry get created along this half 0, 0, 0, half 0, and 0, 0, half, and so on. All these are independent centers of symmetry. That means this center of symmetry, which is at 0, 0, 0, can generate only that object, which is shown as 2. If we want to generate that object onto here, this has to be a different center of symmetry. That means the location of the center of symmetry and also the property that is associated with the center of symmetry is when we refer to this as 0, 0, 0. And once we do that origin definition, then this becomes half, half, half. If this is taken as 0, 0, 0, then the corresponding one here is half and this is half. So effectively, as we mentioned in the last discussion, that this represents the so-called lattice. It is essentially the frame, and we can move the frame down along the A-axis, B-axis in whichever way we would like to. In this particular case, in such a way that we can take this point, call this point as the origin 0, 0, 0, and generate the next unit cell, which will be exactly the same thing. You remember the pictures we saw from Euler's, Escher's diagrams? You recollect that the yellow horse and the white and the red horse, and we saw how those two are related to each other. We can move any point of that horse to any other point. The symmetry remains the same. So this, therefore, is essentially a frame which can now be slid through the entire space. But the dimension of this is given by the unit cell dimensions, A, B, and C in the perpendicular direction. So thus we describe our object along with the crystal system into which it goes into, the equivalent points, the location of the symmetry elements in this unit cell. We can identify the symmetry elements. We can also mark the equivalent points. So this whole set now describes one particular space group, which happens to be now P1 bar. P is the primitive lattice, which is essentially representing the total number of lattice points as 1. And then 1 bar is the symmetry, which generates 2 equivalent points. The property of the center of symmetries in all these cases, suppose we take 0, 0, 0. If the object is now at 0, 0, 0, then x, y, z is 0, 0, 0. X bar, y bar, z bar is also 0, 0, 0. That means it becomes what we call as a special position, where x, y, z and x, y, z bar are one and the same in this particular case, and therefore the number of equivalent points now will be equal to 1. And that is how this becomes a special position. We notice that in this particular space group P1 bar, we have several such positions. Each one of them is a different center of symmetry. This center of symmetry is at half 0, 0. This is at 0, half 0, and so on. A person by name Wyckoff made notations for this, and the notation is such that we take the most symmetric position to be represented by an alphabet A, and we call this particular position as A, maybe this position as B, this position as C, and so on. And this is known as the Wyckoff notation. And with respect to that, we also describe the number of equivalent points which get associated with this. In this particular example, it is 1. We will have to describe all of it in one particular diagram, and that is the one which we will find as the diagram for P1 bar in the international tables for crystallography. So international tables for crystallography is like the Wren and Martin grammar we read for our English language learning. It is something similar. So without the volume A of the international tables for crystallography, we will not be able to really understand and appreciate the nature of symmetry that can be generated in all the 230 space groups. All the 230 space groups are listed there. So we do not have to go through every space group in this particular manner, except that we take a couple of examples. One example is the example P2, which tells us the twofold symmetry. As you see here with respect to this origin, once we have a twofold symmetry, the angles, two of the angles become 90 degrees. So the angle between AB, which is shown here, the projection, C is coming in the other direction. The convention is in monoclinic cells, beta is the non-90 degree angle. So the angle between A and B is gamma, which is 90 degrees. So we will show this as a rectangle. And the twofold axis is now shown in a direction which is along the B direction. So you see that this is the twofold location. It is at 0, 0, 0, 0, 0 is the origin. And with respect to that origin, we have one at half, the other one at 1.5. And the equivalent points, therefore, are x, y, z. And this one is x bar, y, z bar. That means x changes to minus x and z changes to minus z. And this becomes the equivalent point. So you see that again, we translate this by 1 unit to show that it is within the unit cell. So z is equal to 2 again. The number of objects inside the unit cell is 2. Likewise, we can go to the next space group, which is shown here, P21. In this particular case, we have not just a twofold rotation, but a half translation associated with this in such a way that it is like a screw motion. So we have the twofold rotation and then a half translation. As is evident here, we have the twofold rotation and then we translate this object, which was here, for example. This is just a twofold rotation, but this is now moved by half the unit. So it comes and occupies this position. So we have the two equivalent points, x, y, z, x bar, y, plus half z bar. So this is how we understand the pictorial way of representation of the equivalent points on the space group. We will have certain other examples where we have to realize that we can combine, let us say, different things like P21 and a mirror perpendicular to that. This now belongs to the monoclinic symmetry, 2 by m is the point group. 2, 1 by m now is a special case in this space group. So when we associate 2, 1 axis, this now essentially is associated with the unit cell. That means we have to have the unit cell information that has to be associated with it. So we essentially, you have this point, it undergoes a 2-1 symmetry. Now this 2-1 symmetry is a mirror which is perpendicular to the 2-1 axis. So it undergoes a mirror operation. Likewise, here again, there is a mirror. The mirror repeats at half the distance. One of the things we must notice here is whenever we have a non-translational symmetry associated with a translational symmetry, that means there is a half translation associated with the twofold axis. Then we generate a 2 by m symmetry, which is center of symmetry. But now the center of symmetry moves by 1/4. So if this is taken as the origin 0, 0, 0, the center of symmetry is at 1/4 the distance along the b axis, along this direction. So the convention is to use always this as the center of symmetry, as we will see later on. So when we discuss the symmetry, excellent, the symmetry that appears in the given direction. A similar thing happens when we have a 2 by C 2 by C symmetry. A two-fold symmetry associated with the origin. And then we have a 1/4 translation where the center of symmetry gets generated in the direction of C. Excuse me, sorry about that. So this now generates the type of space groups which are listed here: P21 by M, P2 by C, and P21 by C. So one of the things we must notice here is that the special positions in these space groups are those with non-translational components. That means the special position is where the non-translational components are located. The space group P21 by M has a mirror symmetry. So if there is an object which is associated with the mirror symmetry, that is the non-translational component. So if there is any object that comes associated with 1/4 along this direction with 0, 0, 0 now shifted to the origin, whenever we have a center symmetry, we make it the origin by convention. So the mirror by it now shifts by 1/4. 2, 1 remains at the same axis. Similarly, in this case, the 2 by C, the C glide moves, the two-fold rotation stays at the same position. The C glide moves by 1/4. But in the P21 by C case, both the glide as well as the C21 axis move. So that means to say that when we have these special positions, they have to be associated with non-translational components. The non-translational components that are associated here are the mirror symmetry that can coincide at 1/4 position along the C axis, and the 2-1 screw that can coincide with the two-fold symmetry associated with 1/4. So this point is very important, that special positions, those are with non-translational components, will generate the special positions. So let me recapitulate very quickly what we have discussed, because I was coughing in between, so it must have led to some confusion. So let me tell you that in the case where we have a space group P21 upon M, we'll discuss this in full detail so it becomes clear. We have the equivalent points at x, y, z, x bar half plus y, z bar. So x, y, z, we generate the x bar half plus y, z bar. So it is illustrated in number 2. So this 1, 2, 3, and 4, or this 1, 2, 3, and 4. So we generate these 4 objects. Obviously, we want these 2 objects to be taken inside. So we do the translation periodicity operations such that the unit cell now, which extends from this center of symmetry to that one at 1 unit, this one at 1 unit, this one at 1 unit, with additional centers of symmetry appearing at the positions of half. Then we see that there is a mirror symmetry which gets automatically generated at 1/4 the distance. So if any object is associated with this mirror symmetry, or any object is associated with the center of symmetry, those become special positions in which the number of equivalent points, which is z equals 4, will now become z equals 2. There will be 2 points only, because the operations are such that the presence of the mirror symmetry makes it in such a way that the mirror vanishes. So in other words, in this case, it will become x bar, y, z bar. So effectively, it is like a two-fold symmetry. And therefore, we will have a situation where we have a P21 by M symmetry carrying special positions. All these have to be represented once again in one single diagram or one sheet of paper in the international tables for crystallography, which we will examine carefully as we go along. The same logic is extended to non-centrosymmetric systems. The example given here is from an orthorhombic system where we have 3 non-intersecting two-fold axes. Suppose we have 2 intersecting axes. We discussed in the last discussion, based on the Euler's theorem, we will have the third axis also generated. So if we have two two-fold axes intersecting at a point, the third two-fold axis will also get generated with respect to the origin 0, 0, 0. So if we now have two 2-1 screw axis intersecting at a point, as is shown here, there is a 2-1 screw which is occurring at 0.5. There's a 2-1 screw occurring at 0.5 in a direction perpendicular to that, because this is an orthorhombic system. The three angles are 90 degrees with respect to each other. A and B and C need not be equal to each other. So this is 90 degrees in this direction, 90 degrees in this direction. These two, let us say this is the A axis and that is the B axis. They are associated with a two-fold screw. But once they intersect at a point, when they intersect at a point, the equivalent points which we generate, which are shown in this form now, a circle with plus coming up towards you, a circle with minus going down here, which is a result of the 2-1 screw operation in this direction. Similarly, the result of the 2-1 screw operating in this direction is that one. Now, in order to bring these inside the unit cell, we have to move this fellow up here, and this one comes down here. We will see now, it so happens that we generate this point, and the corresponding equivalent of this gets generated as well. So there is a two-fold screw axis which gets generated. So this space group, when we have two intersecting 2-1 screw axis, will be P21, 2-1, 2. Now, how can we generate the space group 2-1, 2-1, 2-1? If we want a space group 2-1, 2-1, 2-1, then all the three axes which we consider, the two-fold axis, two-fold screw axis, should not intersect with each other, but they should be moving with respect to each other 1/4 the distance. So we have, therefore, two non-intersecting sets of screw axes parallel to A and B, which produces a third set of screw axes parallel to C. So this now becomes also a screw axis. You will see half plus 0 here. Here it was just a 0 which is representing the object. So this object now has a two-fold symmetry here. The object here has a 2-1 screw. Once again, when we examine the international tables in detail, I will go back to this and explain it in full. Now let us go to the next slide and take a realistic example. We have been discussing in terms of objects being represented by either a circle or a comma or whatever it is. But what happens when we look at a realistic structure? So we take the case of calcium carbonate, the aragonite form of calcium carbonate, the crystal structure of that has been determined. And it is shown that it belongs to the space group PMCM, which is an orthorhombic system. As you see from here, you can once the space group information is given, you can immediately realize that it is belonging to the orthorhombic system, because there are three axes which can be associated with two folds. A mirror symmetry, a C glide, and an N glide effectively are additional components which can be associated with 2, 2, 2. So this space, the point group, therefore, will be MMM. Remove the translation component, remove the notation for the space group. So a space group PMCN will now generate a system which is MMM as far as point group symmetry is concerned. How does the symmetry operations develop in this? These are two diagrams which show the equivalent points. This is known as the equivalent point diagram, which you will find in the international tables. And this is known as the symmetry diagram. So you see that the mirror symmetry, which is now coming perpendicular to the A-axis, is perpendicular. This is the A-axis. So it comes perpendicular to the A-axis, and by logic, which we discussed earlier, it moves by 1/4 the unit. So this is the location of the mirror. So the mirror is 1/4 away from this particular position. The moment we have the point group symmetry M, it is in fact 2 by M, 2 by M, 2 by M. Automatically, there is a center of symmetry that gets generated. So we have X, Y, Z as the equivalent point. We also have minus X, minus Y, minus Z as its equivalent point. So once we generate equivalent points for this system, you see the C glide is now moved 1/4 away from the origin in the direction of Y, because C glide is along the Y direction. The n glide is shown like this with an arrow coming like this, showing it is a diagonal glide. And that also moves 1/4 away in the direction coming towards you. This is the two-dimensional representation of the three-dimensional space group. So you therefore get in all 8 equivalent positions. These are the ones which are shown inside this box, the eight equivalent positions. And their coordinates are given up here. Now, as we discussed earlier, the non-translation components in this space group, the diagram, if you look at, what are the non-translation component ones? The mirror symmetries, which come here at 1/4 and 3/4, and also the centers of symmetries, which are associated with this 0, 0, 0, and 0, half 0, 0, half 0, half 0, 0, and so on. So there are possibilities of locating an object which is having a symmetry, which is a mirror symmetry. So the object has a mirror symmetry. Then the mirror symmetry associated with the object will coincide with this mirror, and the object can sit here along the mirror. In such a situation, the number of equivalent points reduce from 8 to 4, and these therefore become special positions. I think now this discussion on special position is very clear. These positions are generally having a multiplicity which is different from the general position. The multiplicity means the total number of the z value, in this case is 8, and it reduces to 4 when once the object is associated with a mirror. It reduces to 1 bar symmetry, that is the center of symmetry, when it is associated with 0, 0, 0 and 0, half 0. You see that there are 4 sets of equivalences which come in here, which actually carry the space group information PMCN. So if it is not that, like in P1 bar, we had each one of them a separate special position. In this case, the symmetry associated with the space group decides how many such we can associate with this special position, how many equivalent points we can associate with this special position. So the 8 of them now become 4, and when we have 0, 0, 0, we find that the other 4 points will also be generated by another 1 bar symmetry, but this 1 bar symmetry is now with respect to 0, half 0. So when we now give the Wyckoff symbols, the 0, 0, 0, we get an associated Wyckoff symbol A. 0, half 0 set gets the Wyckoff symbol B. The plus minus 1/4 YZ, this gives the Wyckoff symbol C, and the coordinates associated with general position, the Wyckoff symbol is D. So when you say that an atom is sitting in 1D position in this particular space group, we automatically know it is in a general position. And when we say the atom is associated with 1B position, we automatically know that it is associated with the 1 bar symmetry, which is at 0, half 0. So this is how we picture the objects inside the unit cell, and with the space group conditions with respect to the symmetry diagram and with respect to the equivalent point diagram. So this then is a general overview of how we can visualize a crystal structure. If that is the case, what happens in the case of calcium carbonate? We find that on solving the structure, the cell dimensions are given here. That is not so important. We show the AB projection. And in this particular case, we see that the calcium has a choice. You see, CaCO3 is the molecule. And it turns out that there are 4 such molecules inside the unit cell. The moment we say 4 molecules in the unit cell, we have 8 equivalent points here. So 4 molecules in the unit cell means that the atoms must be sitting in special positions. They cannot be in general positions. The moment they are in general position, our formula will change, because CaCO3, there will be 8 calciums only that are allowed in the unit cell if we are in the general position. And we find that there are 4 molecules of CaCO3. That means there are 4 calcium atoms, 4 carbon atoms, and 12 oxygen atoms. Now, oxygen atoms have a choice. They can either occupy the general 8 positions and one of the special positions, giving 4 equivalent positions. So totally it will be 12. So oxygen can sit in general position, or oxygen can sit in 3 different possible special positions. So the Wyckoff's symbol A, B, and C, and D become very validated here. So the oxygen has a choice between ABC and or one of the ABC and D, so that the total number of oxygens become 12. It so happens that when we solve the structure, we find that one of the oxygens is associated with the mirror and the other oxygen sits in a general position. And this is the projection diagram, which gives the structure of calcium carbonate in 2 dimensions. So it also tells where are the calcium atoms sitting, where are the carbon atoms sitting, and where do we get the coordination of calcium around it with respect to the oxygen atoms. So this is the projection diagram of calcium carbonate structure in the realistic situation. And we see, therefore, the advantage of having molecular symmetry associate itself with the crystal symmetry. And the number of molecules in this case is 4. And therefore, we know that there are only 4 calciums, 4 carbons, 12 oxygens, and we can distribute them among the special as well as in the general position. So this is how the structures develop. So we have now learned how the symmetry is disposed in the unit cell, how the symmetry positions can be associated with special positions, with general positions, and we draw the symmetry diagram. We can draw the equivalent point diagram, and then we can associate atoms with the given system. Having seen that, now we go over and see a slide which is taken from the book of Glusker and Trueblood, a very old book. I think now it is in print again. And this is a wonderful book and a very simple book for the beginners. And this tells us how we can see atoms. So it is an analogy with microscope. When we have a microscope, we have visible light which falls on the object. The object scatters light in all possible directions. And we have the objective lens, which focuses the image of the object. And this image of the object now through the eyepiece lens gets expanded, and we therefore get an enlarged image. So we can see the object in very much detail in positions which we get for the various positions of the atoms, etc., etc. We will see that in another slide, which I consider my signature slide. We will discuss it in the next slide after we finish discussing how the X-rays work. In case of the X-rays, we have an object which again scatters now X radiation in all possible directions. We will show soon that these possible directions are controlled by symmetry. And because of the symmetry and the translational periodicity and other associated symmetry elements, we cannot get the scattering in all possible directions. There are specified directions which are governed by, as we all know already, by Bragg's law. We will see how that comes up, and therefore we get a set of points after they scatter onto the photographic film. This is a old book, as I mentioned. Now, in place of the photographic film, we have now the modern day detectors. We have the CCDs, we have the photon detector, we have image plate or whatever. So this now gives us the intensities of these spots. So what we have to therefore do here is, unfortunately, we do not have a lens. If we want to make a lens for getting this image of the object in glass, the size of the lens will be slightly larger than the size of the Earth. And we have to go in space to find the image of the object. It is essentially a dream which Elon Musk only can satisfy us, not us at this moment. And therefore, we will have to deal with what is called a Fourier synthesis. In order to do the Fourier synthesis, we not only need the intensities, we also have to have the phases that are associated with this, because these are waves which are scattered. That is a separate discussion, which is probably not the scope of this current webinar. That involves the structure determination protocols and so on. So let us assume that we have the phases as well as the intensities that are determined. We do what is known as a Fourier synthesis, which is essentially the job of reconstructing the image, which is done by the lens. So we do the job of the Fourier synthesis, which is a reconstruction of the image. Crystallographer is required at this point, the book says, but then the book is old, as I told you. We need only the computer. In fact, crystallographers are more or less eliminated. They are an eliminated species because they made crystallography, the whole protocol, so simple that now the machines, when once you put the crystal on the machine, the scattering is automatically done. The scattering is analyzed. structure is solved, and you get a picture of the molecule as is shown here on the screen directly in a matter of few hours, if this is a very simple molecule. And so you don't have to do anything. You don't have to be a crystallographer. You don't have to learn the concepts of symmetry in order to do structure determination. And that's how it is becoming. Even though when you cannot solve a structure which has certain difficulties, you need this fellow still. But as I mentioned, this is a disappearing species at this moment. Slowly and surely, crystallographers are replaced by high-speed computers and automatic devices. And of course, the predictions of these structure aspects. Anyway, that's a different story altogether. We do not have time to spend because we are already 40 minutes through. Let us go to my signature slide. And this is the slide which I love most, because everything we want to know about structures will be understood by looking at a loaf of bread. If you go to the baker and then you ask him to make a bread with all additives added to it, he will add, let us say, almonds and raisins and some other things, and then make a dough. He mixes the dough. He doesn't know where the almonds are and where the raisins are. They get thoroughly mixed up in the dough, and then he bakes the bread. The bread, when it is baked in this particular form, comes out in the form of a unit cell. So we can now consider this as a unit cell. The length is, let us say, A, the up direction, let us say, C, and the horizontal direction is B. So a loaf of bread is a unit cell. And this unit cell now repeats itself in 3 dimensions in all directions. So a large number of loaves which are arranged in a bakery, which we see already in bakeries, that is a lattice. And in that lattice, we can have these loaves of bread. So we have the unit cell. Now the additives in the unit cell can be considered as atoms or molecules or ions or whatever. Let's consider them as atoms. So the almonds and the raisins and any other additive which is added to give the taste, those are the ones which we now consider as atoms, and they are distributed inside this loaf of bread. So our job is to find out where these are and what the nature of each one of these additive is. Whether almond is hard and the raisin is soft, how we can identify the individual entities and so on. Similarly, we have different kinds of atoms in the unit cell, and these atoms have to be formed. So what we therefore do is, in the case where we have to find where the almonds are, we slice the bread. So when we slice the bread, is one of these slices, let's say we take it from the center. It may so happen that we are very unlucky because no piece of either the almond or the raisin appears there. It's a flat plate, a flat slice of bread. You are unfortunate. But there may be another slice in which more of this material may be found. So this is what really happens even in the case of the structural determination using unit cell, because what we do is we cannot now do this slicing on the unit cell, and we want the crystal to be intact, and we want to have a non-destructive test. So the way we do that is send in an X-ray beam as a probe, and these X-rays now of the order of 10 to the minus 8 angstroms. And so they will now look at the unit cell as a loaf of bread and a lot of slices through. Imagine that it is not always required to slice the bread this way. We can slice the bread whichever way we want. So this now has to be identified. Each slice has to be identified. This is known as an indexing procedure. So suppose you take this as the A-axis. This point at which the A ends is referred to this particular slice. When cut it off, it is the 100. If we take the slice at half the point, it is half 00, 1/3 is 300, 1/4 is 400, and so on. And these values of 100, 200, 300, 400 are referred to as Miller indices. And these Miller indices are the ones which we will observe in an X-ray diffraction experiment. So when we do the X-ray diffraction experiment, X-rays fall on it. X-rays are focused onto the slice. The slice now scatters or diffracts the radiation. The scattering becomes diffraction because only under certain circumstances, as gone by the Bragg's law, the scattering occurs, and their intensity is as a spot. So we get a collection of spots from each one of these slices, And as I mentioned, it is not always necessary to slice it like this. We can slice it at an angle like this. So 1, 1, 1, one along A, one along B, one along C. That will be the 1, 1, 1 plane. And we can measure the intensity coming from 1, 1, 1 plane. Also notice that since these additives which we have got, these are the atoms inside the unit cell, they can be associated with the plane and they need not be associated with the plane. But when the X-rays fall, the X-rays are essentially scattered by electrons inside the material. They are not scattered by the planes, they are scattered by the electrons inside. And the contribution of each and every electron in the unit cell to that particular plane comes out as the intensity. It so happens that if there are more parts of the electron density of the atom associated with the plane, then more intensity will come from the plane. And that is how you see in a powder diffraction peaks, which are of different heights at different 2 theta values. The 2 theta values are essentially the angle at which the X-rays come and the scattering angle governed by the Bragg's law, which you all know very well. And therefore, we collect now the set of intensities. So this is my signature slide because I think there is a very nice straight comparison between, I believe, the loaf of bread, the additives in the loaf of bread, and the electron density distribution, which is essentially what we would like to map. Eventually, we want to map where the additives are inside this particular unit cell. It so happens just the deviation of a loaf of bread to the next loaf of bread. In this particular case, the unit cell repeats itself in all 3 dimensions. That's the only difference we should remember. And therefore, all loaves of bread are identical in this particular case. Okay. So then we define crystallographic directions, crystallographic planes, and so on. I don't think I have time enough to go through the details. But essentially, you see that we can now have, as I said, P00 along the A direction, 0Q0 along the B direction, 00R along the C direction. So if we now take this plane, it is the intersection of PQR. PQR is the plane. And we can express this plane as in terms of what are known as the Miller indices, which are represented as H, K, and L. And H, K, and L are integers. So these are integral values, and therefore we get integral values of HKL. So the planes inside the unit cell are described in terms of integral numbers. Having got that information, let us see one example where we have a 2-dimensional representation of a 1-1 plane. If we have a 1-1 plane, we have this as the A-axis, this as the B-axis. You see that the 1-1 plane is the one which is the diagonal. It passes through like this. So this is a set of parallel 1-1 planes. Okay. And on the other hand, if you want the 1-2, you see that there is a halfway point up here, and this now represents the 1-2 plane. And the 1-0 plane is the one which never cuts the y-axis, as is demonstrated here. Now, as we already said, that it is the electron density which participates in the diffraction experiment. So if we have an atom, it is the atom which scatters. So if we have 2 atoms, 2 different kinds of atoms, and these atoms are together forming a diatomic structure, let us say, the scattering is coming from them. This is how they are arranged in the unit cell. But what we measure is the diffraction coming from the planes, which essentially define the lattice. So with respect to each and every lattice point shown here, we have the associated structure. So the scattering from each and individual atoms now constructively or destructively add up, and we have the Bragg's condition, which is satisfied. I'm not going into the description of how we get the Bragg's law, but we know that we do get 2d sine theta equals lambda as the expression for the Bragg's law. I think we are running out of time, so I will go faster. If you have questions, you are most welcome to ask me as we go along, but I'll take 5 more minutes to finish off what I would like to say. So we have, for example, in this case, a direct unit cell is in red. The planes are indicated in the blue. And the experiment which we do by X-ray diffraction will give us the so-called reciprocal lattice. That means what we get are these spots here, which is essentially representing the reciprocal nature. That is because we have taken, for example, when we cut that slice, we took 100 then half point slice was 200, 1/3 point slice was 300. So the Miller indices now represent the so-called H and K values, which are in a different space than the main direct space. So we have the reciprocal space. The relationship between the reciprocal space and the direct space is evaluated in terms of what we call as an evolved sphere construction. I will go through that very quickly to tell you that if this is the direction of the X-ray beam, and let us say this is the background now represents the reciprocal lattice, and we take this point as the origin of the reciprocal lattice. We have the direct beam going like that, and we now see that this is called the evolved sphere. And whenever the evolved sphere cuts the reciprocal lattice point, evolved sphere is 1 divided by lambda. That is because we have 2d sine theta is lambda. So this is in reciprocal space when we take 1 by lambda as the diameter of this evolved sphere. Whenever this point P now intersects with the circle, we get this is the circle, but in 3 dimensions, it's a sphere. So whenever it cuts, we get the diffraction. And that's how we get spots. And so we have, therefore, a collection of these spots which obey certain rules and certain regulations, which essentially cover the description of the reciprocal lattice, and therefore follow the Bragg's law, and we get the spots in the experiment. Now back to the space groups, the international tables, we take P1 bar. As I mentioned, this is the symmetry diagram. It shows all the symmetry positions that can occur and in 3 different projections. And this is the equivalent point diagram, which we already saw. P1 bar is very straightforward and simple. There are 2 equivalent points and there is special positions. And all these get listed like this. We have 2. And this is what we call as the Wyckoff's letter. We already discussed that in detail. And we have X, Y, Z, X bar, Y bar, Z bar, representing the general positions. It so happens that these conditions are reflected in the data which we collect also. Since there is no translational component associated with P1 bar, we do not get any special, what we call as systematic absences, which get associated with reflections. So we do not get any of those. On the other hand, if we look at P21 upon C, the symmetry diagram is shown here, we see that we do have special positions, A, B, C, D, corresponding to these, and we have equivalent points which are now involving translation components. And whenever we have translation components, we will now end up with the reflection conditions. We have HOL, L odd absent, 0K0, K odd absent as the systematic absences. That means in the list of HKL reflections which you have, the projection reflections HOL will appear, and also the 0K0, which are the axial reflections. The value of K will now be 2, 4, 6, 8, and so on. Only those will appear. And in the case of HOL, only the even values of L will appear, indicating the presence of the C glide and indicating the presence of the two-fold axis, 2-1 screw axis. The two-fold axis, the mirror symmetry and the 1 bar symmetry will have no systematic absences. Systematic absences appear only in case we have the translational component that is associated with it. Obviously, when we have translation components associated describing the lattice, like the C centering, A centering, F centering, and I centering, these centering of the lattices also will give general absences. They show absences in general reflections. So this is an example in 2-2-2-1, 2-1, 2-1, even though it is a non-center symmetric space group. We already discussed and showed the equivalent point diagram. And in this case, again, we will have systematic absences occurring due to the presence of the 2-1 screw axis, which are intersecting with each other. So the next issue is, of course, the presence of the atom, but I think I'm running out of time. So I will tell you one aspect which we must remember. As the scattering angle changes, the contribution from individual atoms to the scattering keeps reducing. And this is a very negative factor, and this has to be properly evaluated and corrected. And that is an issue which we will have to discuss probably in another talk. So coming to the discussion of how I wanted to tell you how we get a powder pattern, but I think I'm running out of time. Definitely now, we have only 4 minutes left. So we have, of course, discussed these these crucial issues: three-dimensional objects and representation of stereographic projections. We have discussed understanding symmetry. We have discussed the issue of the pictorial illustration of symmetry operations. We have talked about periodicity and space groups. We have also discussed a few issues which are associated with diffraction patterns. One issue which we have not discussed in detail is the incorporation of symmetry, which is associated with diffraction. So more or less, all queries have been addressed. I must tell you that this is a course which spans over 20 odd classes of 1.5 hours each. And therefore, we have covered the whole thing in 2 hours. And obviously, we have to be rushing towards the end as always. And we have anyway, I believe, have reached some kind of a goal, not like the goal which was reached today by Argentina against Saudi Arabia. Anyhow, these are the textbooks which I recommend, which you must study, which will also have all the details which we discussed. This book in particular has all the details of whatever we have discussed. This is a wonderful book. Unfortunately, I am told that this is out of print, but if any of you can get hold of it, please see this book. This is the one which will tell you about all the symmetry aspects thoroughly and completely. And of course, all these books add up to the knowledge which we have gained in structure determination aspects. And of course, the Bible or Quran or Bhagavad Gita or whatever you want to call it, it is the international tables for crystallography volume A, without which we will not survive the structure determination aspects associated with our work. And I think with this, I would like to stop and take any questions which are there. And thank you for your patience.
All right. Thank you, Guru. Excellent presentation. Trying to get several weeks of a course in an hour. And we thank you for your presentation. There are a number of questions, and we won't have time to answer all of them, but what we will do is the questions will be provided, and amongst the staff, and in particular, Professor Rao, we'll get those answered and they'll be sent out to everybody. Guru, could you put your last slide up of the books that you were talking about? Because there were some questions, I believe. Just to clarify, the next slide, please. I think just to make sure, you had mentioned about the in the middle of your presentation, you were talking about sort of the introductory book or introductory that you said maybe was out of print, but maybe back in print again. Could you please elaborate on that, please?
This is the book of Duncan McKee and Christine McKee, this book, The Essentials of Crystallography. And this is a book which I have a copy of it from some time ago. And I tried to get a new copy from the library and later also from a bookstore. But the guys in the bookstore made a lot of efforts to get this book, and apparently it is out of print. This is originally printed by Oxford University Press. And these two, it's actually a husband and wife team. They were both crystallographers, and they wrote this book several years ago, maybe in the early 60s or so on. Most of the discussion which I had on the way in which the symmetry develops, the equivalent points develop, the pictorial representations, and so on, they are present in this book. And so I would love to have this book with everyone who are practicing crystallographers. So this is the book I was referring to.
Okay. All right. So let's maybe we have time for one question here, Guru, and then the others you'll be able to answer for everyone offline. Appreciate that. Let's go. I'm just looking at some of them that were asked here. Well, just for everyone's information, will the recordings be made available to the webinar participants? The answer is yes. You'll get information on how to connect to the ICDD website and what the link will be for that. There's a question here about what is isomorphic subgroups?
Okay, I had very little time to cover the details of the international tables, but let me go there. Take one example here. So we have an entry here, the maximal non-isomorphic subgroups. So this is where the effective way in which, for example, this is listed under the P21 upon C. So let's take P21 upon C as the discussion space group. And in P21 upon C, we have the equivalent points listed here, and the symmetry of special projections are also listed here. Then we have the maximal non-isomorphous subgroups. Now, in this, it is given, the first is the P1C1, PC7, 1:4, and P1211, 1:2, and P1 bar 2, 1:3. Now, what it means is that these subgroups are the possible suggestions for equivalences associated with the main crystal system. So we have P21 upon C as the main crystal system. So we can have, for example, the space group PC and the space group P2 and the space group P1 bar. They can also be a part and parcel of this main space group P21 upon C in this following ratio: 1:4, 1:2, and 1:3. It's not the ratio, but then if we have P21 upon C, effectively, we can take PC, combine 4 subgroups of these CP. That means we can have this P21 upon C divided into 4 blocks in the unit cell. So if we go back to the previous diagram, we can now divide this into 4 blocks, and each of these blocks will be, let us say, 1 unit, and that will represent the space group PC. So that is what is meant by a subgroup. The advantage here is it may so happen that we may have different kinds of structures going into P21 upon C, and with modulations and so on. I think people who work on modulations know about subgroups in more detail. I think Suji in ICDD has a very good knowledge of this area. I am not very conversant with the details of how to describe the maximal isomorphic subgroup with lowest index and non-isomorphic subgroups and so on. But basically, the non-isomorphous subgroups represent the way in which we can subdivide the P21 upon C unit cell, such that we can have representations of 4 such units in PC, 2 such units in P21, and 3 such units in P1 bar, something like that. If I am answered correctly, I'm not very sure whether the answer is correct. If Suri is there, maybe he will be able to answer.
All right. So what we're going to do now is that we have used our time for the presentation, and we do thank Professor Rao for the excellent presentation. We will be taking the questions that were asked, putting them together. They will be addressed, and then they'll be sent to all the participants who are here today. I'd like to thank you, Professor Rao, for the presentation. And it might be possible we might be talking about a part 3, because clearly there's a lot of information and a lot of interest.
Don't forget to like and follow ICDD on Twitter, Instagram, LinkedIn, and Facebook. More information on icdd.com. Contact us at info@icdd.com.